In this video, we're going to discuss some of the knowledge necessary to complete Worksheet 3 of the ETM packet, which focuses on force versus displacement graphs and using those graphs to come up with the energy stored in a spring or, as we'll learn later, the work that is done by a specific force. Starting off, we're given an equation for a spring force, saying that a lab group found that the spring force is equal to 1,000 newtons per meter times the displacement. We're asked to construct a graphical representation of this force versus the displacement using the axes that are given. The first thing I have to decide is exactly what my scale should be. I'm going to look at parts A and B for that. Notice in part A, it's asking about the amount of energy stored as x goes from 0 to 10 centimeters. And then in part B, it's going from 15 to 25 centimeters. That means I know that my horizontal axis should go from 0 to 25 centimeters. Now, of course, spring constant is in newtons per meter, so I'm going to need to convert those. Remember that there are 100 centimeters in 1 meter, so 5 centimeters would be equal to 0.05 meters. 10 centimeters would be 0.1 meters. 15 is 0.15. 20 is 0.2. And 25 is 0.25. And I will make sure to label my unit as being meters. To decide what scale I need on my force or my vertical axis, I'm going to think about what's the highest my value would be. When I multiply 1,000 times 0.25, I get 250. That means that 250 is going to be my highest value. And I'll go down from there. So I'll mark that as 200 and 150. 150. Remember, in physics, we always want to start with our origin being 0, 0. I also want to make sure that I put my units there as being newtons. Now I can plot my points. So 1,000 times 0.05 would be equal to 50. And 1,000 times 0.1 is equal to 100. 1,000 times 0.15 equals 150. 1,000 times 0.2 equals 200. And 1,000 times 0.25 equals 250. So if I were to graph this, I would get a straight line, a nice linear graph, as shown here. To determine the amount of energy that's stored while stretching the spring that's described, we're going to find the area between the graph and the horizontal axis, much like we've done before. It says from when the spring is stretched from x equals 0 to x equals 10 centimeters. So the area that I care about would be this area shaded right now. We've got a nice triangle there. Finding that area would be finding the area of a triangle, which we know is 1/2 base times height. And since we're talking about the amount of energy that's stored while stretching the spring, we would call that elastic potential energy. So 1/2, the base we know is x, and the height we know is our F, force. And so it would be 1/2. My base is 0.1 meters. And my force, or my height there, is 100 newtons. This gives me 5 joules of energy, because 1/2 times 0.1 times 100 equals 5. Now, a really important takeaway from this worksheet is the fact that this is also equal to the work that is done to stretch the spring that amount. We could say that's the work done by the spring force there. So key important thing here, to find the work that's done by a force, you're going to find the area between the graph and the horizontal axis on a force versus displacement graph. Let's try that one more time in part B. Part B says to determine the amount of energy that's stored while stretching the spring described from 15 centimeters to 25 centimeters. Again, the thing I care about is the area, but this time I'm going from 15 to 25. So we're going to look at the area of this shape that I'm drawing right now. I'll kind of shade that in a little bit so we can see that's the area that we care about. I could split this area up into two parts. One of those parts would be a rectangle. One of those parts would be this triangle that you see up here. And that's what I'll do to find that area. Splitting that up into two parts. So in the first, I have that rectangle. And the area of the rectangle is equal to length times width. Again, this is equal to the electrical energy. So the length of my rectangle goes from 0.15 to 0.25, which means it has a length of 0.1 meters. And it has a height that goes from 0 to 150 newtons. So I'm multiplying that times 150. I have to add to that my area of my triangle that I have, which we know is 1/2 base times height. We have the same base as we did for the rectangle, so 0.10 meters. The height in this case goes from 150 to 250, or 100 newtons. 0.1 times 150 gives me 15 joules, because a newton times a meter is a joule. And 1/2 times 0.1 times 100 gives me 5 joules. So the total energy here would be 20 joules. Again, that's equal to the work that was done to stretch that spring. You'll use this concept, the idea of graphing the force versus the displacement, and then finding the area between that curve and the horizontal axis to find the potential energy or the work that is done in many cases throughout this worksheet.